Okay, so we're almost ready to start. I'll wait for a couple more minutes before it's like 3 o'clock sharp, and then I'll begin. Okay, so let's begin. So first of all, I'm going to tell a little bit about what I'm going to be building. So this is a game, as I mentioned in my announcement, and this is a game in which you can get to be a comparative historical linguist. So why is this? Why would someone care to be a historical comparative linguist, and why would that be interesting to play as a game? So linguistics is actually an area that I've been fascinated in for quite a while, and I studied Latin and Ancient Greek in school, and I studied like Spanish, Latin, Spanish, Italian, and French at various points later. And essentially, to me, this idea of a language family that is that evolves, that is comprised of multiple languages that are derived from each other, it's very fascinating. And there's an area of science which studies this, which studies how the languages relate to each other, how the original languages that were spoken previously, even before Ancient Greek and Latin, how they would have sounded and how they would have looked. So essentially, they try to restore the way the languages were spoken like many thousands of years ago. And this sometimes ends up in games as well. So, for example, there is this game called the Far Cry Primal, where they have actually hired a linguist to reconstruct two different versions of the Indo-European language, like the predecessor of Latin and like Latin, Greek, and Sanskrit, and all the languages that we speak now in Europe, or most of them rather. So yeah, at least in some cases this can be fun. But making actual contributions to comparative historical linguistics requires a tremendous amount of study in order to propose a new credible theory covering like some specific word or some specific word correspondence between different languages. You have to learn so much that I will essentially never have time to study this much linguistics. So I decided to make a sandbox in which it's easier to play with this without learning so much in advance. There's as I mentioned, there are real languages where this comes into play. There are also invented languages where people have built the whole language families, and probably the most well-known example of this is John Ronald Tolkien's Elven languages, where he has Quenya and Sindarin as late modern languages, and also a bunch of languages that have come that existed before them. And they also all have like regular sound correspondence. So by knowing how a word looks in one language, you can try to understand how it looked in another language. And essentially what I'm doing here is I'm building a similar kind of sandbox that models an evolution of a language model, of a language family. Now, how is this a game? So the game, first of all, is to reconstruct again these correspondences between words, so you can see how words in more recent languages look, and you can get some examples of how words in older languages look, and based on that you can reconstruct like the whole system going backwards in time. Why would this be fun to play? So originally, when I came up with this idea, I decided to make a like more or less regular roguelike game out of this. So this language model would be the foundation of the magic system. So you can cast spells by typing like sentences in these constructed languages. And the older the language is, the more powerful your spell is. Like the more magic of the ancients is more powerful than what like people can do today. And I started building it. I built a language model with the help of my friend who actually studied studied linguistics in the university. So she actually knows how these things work in much more detail than I do. And so I started building a game, and I did not get very far, unfortunately, because well, for one reason, because C++, and for other reasons as well. And now I'm trying to reconstruct the core mechanic of this, like just this language stuff, as essentially a web application where you can just play with guessing words. And I'm going to publish this, and I'm going to try to make this at least somewhat fun to play. And if this works as a core game mechanic, then I can probably proceed with maybe building the rest of the game. And if it's not fun to play, then, well, then come up with some other idea. Okay, so this was for the introduction. Now let's actually start with the project. So the name of the project is Hilangro, which stands for Historical Languages Roguelike. And I have the source code of the C++ version somewhere. I'll be referring to it multiple times. And I'll start with a Kotlin rewrite from scratch. So now, of course, as someone who works on Kotlin, who has worked on Kotlin and IntelliJ for a long time, I'll try to draw attention to various IntelliJ and Kotlin features that I'm using. But in the end, yes, it's not rehearsed. It's not like a JetBrains sponsored thing. It's just something that I'm working on as a spare time project. And in the end, I want to build my game, and like this. So this is just real development, not rehearsed, not anything. So let's begin. Create new project. So I'm choosing Gradle, Kotlin, Java. Next. So once again, the name of the project. And immediately there's a tip. When you are creating a new Gradle project, check this checkbox: create directories for empty content roots automatically. So if you do that, then IntelliJ will create a default directory structure for you right away, and you will not be confused trying to guess where to put your Kotlin files in the new project that you have built. So yes, this will be my project in this location, and it's a new directory. And here we go. So before I begin with the project, I'm going to show like some of the code or data from the original version so that you can actually see what we are going to be rebuilding now. So first of all, we have this huge JSON file, which is the language model. So this works as the basis for generating the whole language family that you are going to be researching. So, of course, to make this game fun to play, the language model is not just built in advance. It's randomized, and every time you start a new game, you will get different sounding words. They are still similar, and we were still trying to make sure that Elven sounds like Elven, and Dwarvish sounds like Dwarvish, and Orcish sounds somewhat like Orcish might sound, or people traditionally think of Orcish sounds. But obviously, the actual sounds can differ. So what do we have here? We have these essentially concepts. Those are the words that exist in our language family. And as you can see, so the concepts have names. So this is actually the English word corresponding to the concept. It has a part of speech. So we have verbs. We have like auditives, like pronouns, something like pronouns. We have nouns, yeah, and a bunch of other stuff, pronouns. And we have the definitions of the languages themselves. So, like names. Then we have phonemes. So this is the difference. These are the different sounds that exist in the language. So we once again, they are different every time we start a new game. But these are like the different possibilities that exist for sounds to exist. And phonotactics essentially defines the structure of a word. So how you can combine vowels and consonants so that the word will sound nice in the language that in that particular language. So different languages have different rules for how different sounds can go together in a syllable. And here we are modeling these kinds of rules in our system. So as you see, like Thig, the language of the gods, is the root language in our system. And then we have various languages derived from it, like the elemental language. Then we have the Animish language, which is used by different spirits. Then we have like the ancient Fey language and ancient mortal language, and so on and so forth. And the key part in every language is the set of transformation rules, which essentially defines, so for example, if there is a W sound in the Animish language, so this like the parent of ancient Fey is Animish. If there is a W sound in the Animish, then in ancient Fey it becomes Hu, like HW. And this type of correspondence is sometimes that exists in natural languages, and actually most of the rules in those tables are rules that exist in some or another really existing language. And like there are different kinds of conditions where some rules apply, and once again this also follows the way like real languages work. But this is like essentially this sandbox. So what I'm going to do first of all is I'm going to model the structure of this language model as a set of Kotlin classes. So I have a bunch of C++ code that implements it. So once again, let me open some of the previous files. So that's language model.h. So this is the original C++ implementation. So I was trying to use like a modern C++ style. So I think there is not a single delete statement in the whole code base. So this is all like smart pointers and collection classes and so on. But yes, it's nice, but at some point this gets tedious. So I actually got stuck implementing the dungeon construction rules. So if you want to have so essentially you want to create a map of like various rooms connected by corridors, and you want this to be interesting and not very repetitive. And this was not a trivial piece for me to implement, so I essentially started and then got stuck at that point. But this is going to be a while before I get to this in this incarnation of this project. Okay, so please increase font. Let me increase the font. I hope this is better. So we have this. We have the set of C++ classes, and we are going to start essentially rewriting them in Kotlin. So this may not be like the most interesting part of the project, but still, I think there will be interesting things to show there. So I'll start with the concepts. Let me try to adjust my microphone. Is this better now? Sorry for the microphone issues. It's my first time streaming with this setup, so I haven't yet tried. I haven't yet run into all the, haven't yet sorted out all of the issues. So start with a new file, and this will be called language model. So once again, in Kotlin, you don't have to follow the directory structure with the package structure. So I'm just creating this so I'm just putting the files in the root directory and setting up, defining the classes somewhere. So what's a concept? So a concept has a name, a part of speech, and a bunch of other stuff. So I'm going to, before I move on with this, I'm going to build a CLI interface so that you can actually play with this thing. So and just define the main function. So I'm using a live template here. Now I'm going to copy this JSON file to this project. Can I do it like this? I'm not sure. Okay, so now we have the language model here, and I'm going to start building this. So I'm defining a language model class. And it's going to have a from JSON method. And now I'm going to add a dependency on Jackson so that I can actually use this dependencies. And the latest version is 2.8.6. Now I'm going to re-import the changes. So now I'm going to need a JSON reader. How does this work? Why doesn't it work? So I'm going to just need a new file. So now that I have a companion object, I can use the quick fix to create a method, and this is actually not very nice, so should be able to create a companion object for me automatically, but it doesn't. Language model. So now let's have some concept. So I'm going to use TDD for some parts of this, but at this point I think it's too early to try to write any tests. So for this kind of code, I think it's just easier to test them like this in this way, just by doing stuff manually and seeing that I get the correct results. And create a property. No, it's not a constructor parameter. Create a member property, and it's a list of. Let's make it. Let's make it like this. It's easier. So now let's try reading some stuff. So we'll have a new object mapper, and this is a Jackson object mapper, and I'm not going to use the serializers because, as you can see, the structure I'm not going to use data binding because the structure of JSON is not very uniform, so there are like different as you can see, like the values for each key can have different structure depending on what I wanted to put there. So I'm going to use this. I'm going to use the tree model API to access it, and I think this is just easier to work with this as a graph of object nodes. So we tree and just pass in the file. Let's make it like this. So let's make it regular list of concept, not mutable. Let's make it like a structural parameter. So we have these concepts. Yes, and there is a list of objects that I'm going to. So this should work. Now, once again, it has a companion object, and it's actually a not nullable JSON node. And this is going to be a data class so that we can get a nice toString for free. So what does the concept have? So the data classes are required to have sets of to have some kind of properties, and the properties that we have here are, so we start with a name, just dump the names of everything. And let's try to do it this way. So yes, I'm just ignoring all this. What can you do with a JSON node to convert it to? Sorry, lost my chat window. Yeah, so these blue underlines are a feature of IntelliJ 2017.1. I'm using the release candidate version, which was published on sometime last week, and this is going to be released next week as a final release. Right, it's called stext. Wonderful. Okay, so now we should have enough to try running this thing. And Now it's probably, I'm not sure if it's probably going to fail because the working directory will not be set in the run configuration. No, it actually works. Great. So you see that we have successfully read the concepts that exist in this file. So now let me try to quickly implement the rest of this stuff. So this is just like run-of-the-mill serialization code. So this might be somewhat boring. So you can, if you get bored, just ask me something, and I will tell you something about the project or about some other stuff about Kotlin. So let's deal with the parts of speech now. So we have these, just copy and paste some C++ code into Kotlin file. So there is no C++ to Kotlin converter, unlike the Java to Kotlin converter. But yeah, so this is so now we're gonna set up a map so that, because we are not using the complete names like honorific and hortative in the JSON file, because these are too long to type. So we'll make a map from the names that we use in JSON to the actual enum values. So we're using verb, we're using hort to hortative, then we have hon for honorifics, then we have would to order, and I think the rest are just spelled as is. So I'm just using this map of function and a bunch of infix functions. So each of these two functions, you are probably familiar with this pattern. So the two function is an infix function that creates a pair of the elements on the right and on the left, on the left and on the right. And so the map of function combines this list of pairs into a map. So text, and the default value is none. And now I'm going to convert using the map, and for the values that do not exist in the map, I'm going to use the regular enum value of construct. So the part of speech will be POS name, or if there is nothing there, I'm using the else operator to handle the case when there's nothing there, or part of speech value of POS name. And so now let's run the CLI again, and to make this somewhat easier to read, I'm going to use a join to string function with a separator of new line character, so that we get one part of speech per line. And apparently, yes, so C is a verb, please is a honorific, object is a noun, so yeah, this works. Okay, so what else do we have? Classes are just integers. So classes are essentially an equivalent of so many languages have different declensions, like Latin has 5 different declensions. So like the words that end in us, they are modified in cases in one way, and the words that end in are modified in another way. And this is maybe entirely unfamiliar for speakers of English, because in English there are no cases and no declensions. and so it functions much easier. But in most European languages, there is actually a system of cases, and the words with different endings, they essentially work differently in different cases, and they also evolve differently between from one language to another. So this is why this system also implements these classes. So yeah, this is very the class is very easy to add. So I'm using this word class because class is an identifier, and I can write it like this. But I don't really like these backticks, so I'm just using a long name for this. So what else is there in the concept? So there's also like phonotactics appears in. So there's a bunch of tags. Let's deal with the tags. Text. So I'm using this safe call operator. So if there is a node with the name of tags, then I'm going to map those tags to text. And if there's no such node, then this concept will not have any tags. And so what else do we have? We have phonotactics. What's a I wonder how we use phonotactics. So let me open the implementation file for this. So of course we have a C++ IDE called Cider. No, not called CLine. Yeah, so sorry, I'm getting confused. Called CLine, but I'm not using it. I'm just like there's not much value in trying to get this set up for this project because I'm just reading code. So I'm just using the built-in syntax highlighting for C++ files that IntelliJ community has. I still don't see where it's accessed. Yes. So every language can have different sets of rules for essentially building words, and essentially the phonotactics chooses which set of rules I'm going to use. And the sets of rules are simply identified by names, and like there is this default like main name. So okay, so I'm just going to do this. So this is very easy. So we finally have a nullable item. Question mark. I'm going to close this to have some more space. It's actually, yeah, spelled like this. String, text. So I don't need to do anything to deal with the null case. So I'm just using the safe call operator. So if there's no such node, then it will just be null, and it's okay to pass null to this because it's a nullable string. What else do we have here in this original file? Appears in. Let's do appears in. So appears in is kind of is intended to model concepts which appear in like later languages, like those gods. They did not need to open or shut anything. They just essentially everything was open to them by default. So unlike classes in Kotlin, so yeah, and those spirits have needed to come up with a word for the idea of opening and closing things. So that's why it appears in a like different language. And once again, so this is an optional string. So and so now for this class, I could have probably used just the mapper, because it's like this logic is not too fancy. Well, maybe this part is fancy. But for the other classes, I'm definitely going to need to work with the maps directly. So I think this covers the concept. So let me check the C++ class. So concept appears in exclusive to, so there's also exclusive to. Yeah, so for the particular concept, so for example, this elves, so essentially this is intended to model the like self names of different peoples. So elves call themselves elves, and dwarves call themselves dwarves, and these words exist only in those languages. They are always the same, they are not generated. And as you can see, this is very closely inspired by Quenya, and this definitely looks dwarvish, and this looks, I don't know, like what? Scale folk. Yeah, lizard man. Okay, so I'm going to just add these two little strings, and then we can actually be done with the concepts at least. So I don't like copy paste, so I'm going actually to make a local function for this. So I have the JSON and so I'm going to use it here. And here. And I didn't close my quote correctly. So as you can see, it's so by like putting this one single line of code into a local function, I have removed the need to repeat the JSON node and the as text. And so of course, in this local function, I can refer to the parameters of the enclosing function, so I don't need to bother with passing them around, and this is just all very compact and nice. And I'm actually going to inline those so that I don't have that much code, and I'm actually going to inline this one. So the inline method refactor, so the inline local variable refactoring is actually implemented in the current version, and inline method is going to appear in 1.2. And we also have exclusive to, and we have translation. Okay, so now we have this complete list of concepts. I can verify that this works by starting the run configuration. And I'm getting a null pointer exception because not every word has a class. So I'm going to deal with this. And you can see that these exclusive to and translation have correctly been loaded, and the appears in are also loaded. Yep, everything is nice. So now let's proceed further, and let's start reading the data below that. So we're done with the concepts. I'm going to fold them, and the next is languages and phonotactics. Now this is interesting. So, and as you can see, there is a whole bunch of stuff in the underlying C++ class that, there's a whole bunch of stuff here. And we are going to need all of it. let's try to deal with it. So let's start simple. So we have this concept, and I'm going to fold it, and this language is going to be a data class. Yeah, why not? Just start with a name. And this model also has a list of languages, as you can see. And I'm going to use the same pattern. So now we are reading the languages as a list from JSON. I cannot type languages. And yes, companion object, create member function. Yes, wonderful. And once again, I'm using this. I'm going to use the same map trick that I used here. So I'm going I'm going to convert this to an expression body. It's easier to read this way. And I could even extract a base class out of this and just put this code in a base class, but just for this one function, it doesn't make sense. So yes, companion objects in Kotlin can have base classes, so you can actually inherit some functionality from them. And they can even implement interfaces, and you can pass instances of companion objects around. Fun stuff, but not something that we need here. And yes, once again, create from usage prefix currently does not work for callable references, and this is a known issue which is going to be fixed soon. So I'm going to redo this manually. JSON node is a JSON node, and the result is a language, and the language has a name, and the language has a name. That's it. And what's wrong? Read from JSON, read from JSON. Now it's all right. No? List of language. Yes, now it's all right. And let's see what we got. Now let's print the languages instead of concepts, because we have seen the concepts already. And this is all the languages we have. The language of gods, the language of elementals, the language of spirits, and yeah, so on. Various forms of human languages, elves, dwarves, kobolds, like the traditional set of fantasy peoples. Now let's try to actually build a word in one of these languages so that we can see what this whole thing is about. And in order to read the word, we first of all need to know what the phonemes are, like what different sounds can be in a language. And this is where the JSON structure gets fancy. So I don't actually even remember all of these details, like why those things exist. So the original code was written like 2 or 3 years ago. And even though I did all the implementation myself, I don't remember all the details. Okay, let's see the implementation in C++. So what's a phoneme? A phoneme table. So the phoneme table actually maps a character. So this is like, so stream is offline. Why is the stream offline? Is it offline? Offline. Let me try to restart it. Is it now online? Okay, so I assume that the stream is now live again. And so, okay, so let's get back to our phoneme table and to, okay, and try to implement this phoneme table class. So there is a character that identifies the phoneme, and there are different variants that are given after the character. And yes, let's essentially mirror this now. And the language has a phoneme table. And the phoneme, what does the phoneme table have? The phoneme table has a map for a character to a phoneme set. So let's define a class for the phoneme set. And it has this and you can, and it also has a companion object, and it has a read from JSON method. And which returns a phoneme table, and phoneme table read from JSON is a node of phonemes. So I can type, but this is not something very uncommon. Okay, so yes. Like this. I'm actually going to fix the formatter so that it does not generate those continuation indents, like double size indents in as many places, because I don't find them to be very useful. So now we have, so what do we have in the JSON? We have essentially, how do we actually process this using Jackson? I don't actually know. So this is an so this is a JSON node, and what can we do it with this? I should actually connect the, can I use this? Yes, I can use this. And I can also use this to see the file structure. Yes, this is what I need. I need to traverse the key value pairs. And so I'm going to use this destruction declaration. So now this key will correspond to this string that I have here. And this phoneme will be this. So this will be either an object or an array, depending on what I have in the original JSON. And in an object, I also can have a bunch of various stuff here. So So just make it simple. Result mutable map of from character to phoneme set. So once again, note this pattern. So while I'm reading the data, I have to actually use a mutable collection in order to put the data I'm reading into that collection. And once I'm done reading the data, I no longer like the rest of the thing is immutable. So I'm just using an immutable map, or rather read-only map for the rest of the data. This applies here for the map, and this also applies in, like here I have a read-only list of concepts, a read-only list of languages. So all of the stuff mutates only during reading and then remains read-only for the rest of the time. So set key first. So this takes the first character out of the string because here the key is a character and this JSON, the thing that comes from JSON is a string. Equals phoneme set. You can probably guess what I'm going to read right here. Read from JSON. Phoneme set. And I'm going to return this whole thing back here. And now what is a phoneme set actually? Why doesn't it compile? Character. What? Because I'm not returning a value here. So how do I read a phoneme set? Let's check the original C++ implementation. So if it's an array, then okay. Okay, so the idea is the following. So sometimes, so normally the phonemes work like this. So every time, so like this represents a set of vowels in the language. So every time we need to use a vowel in a word that we are generating, like for example, this V responds to a vowel. Then I'm going to take a random value out of the vowels array. So, so this will be either an A or a U or an E or an O. Now, what's the sticky thing for? The sticky thing works differently. So, so when a phoneme is marked as sticky, then when the language model is generated, like we choose what of those diphthongs exist in the language. So it either has the OR diphthong or it has an AO diphthong. And this choice just remains forever. So we are not choosing randomly either of those tokens every time we are generating a word. We are making this choice while we are loading the model. And this is represented by this code. So directly while we are reading the JSON, we are just selecting the random value. Okay, so let's try to re-implement this logic. So phoneme set is essentially, it's very simple. The phoneme set is just essentially a list of strings which are the possible values for this phoneme. And choices is a list of strings. And so if it's an array, then just returning the phoneme set out of map just text. So you're just mapping creating a string out of each of these nodes. And otherwise, otherwise we have the choices and the sticky flag. So we have the choices and we have the sticky flag, which is so if sticky as boolean false. So if sticky is not specified, then we assume it's false. I think this is what the C++ implementation always requires this to be specified. So if it's sticky, then choices, then choice equals choices. So once again, we are mapping this to strings because this is what they are. This returns. Oh, there should be a function for creating a random element, for selecting a random element out of an array. Is there something random? I lost my chat again. Yep. So now we have chosen the thing that we need from the element, and now we're just returning a phoneme set with this single element list, which we are creating using the list of function. So now it's not sticky, and we just okay. So now that we have that, let's try to read the second part of the rules, which is the phonotactics list. And yes, this is so essentially. So here we have the different like rule sets that we mentioned before, like the main and the part. And for each rule set, like this is like this identifies the phonemes that we use. So if it's an uppercase, then it refers to a phoneme out of this list. If it's a lowercase, it's just the letter I. So like this is just a literal letter that is specified in the JSON table. Okay, so this is actually a map from string to this phonotactics object. So phonotactics. And here fields. I think we had a nice function to. What's the type of this? So this is an iterator. This sounds unfortunate that this is an iterator. Okay, then this is not going to be a fancy map. This is going to be a regular loop of the collection. So this once again, this is mutable because we are reading the data from string to tactics. I hope the problem domain makes sense to at least some of you, because I understand that this is linguistics, and like all these words, they might not make sense. So if they don't, just focus on the Kotlin code that I'm writing. Okay, so do we have this map, and now we iterate over the fields, name, value in JSON, and fields. So now it's very simple, equals from JSON. Okay. So once again, we have a companion object here, and it has a name from JSON. Node, which returns a format tactic instance. Now we can see what this instance consists of. So it has a phoneme table, which comes from the language. And it has a list of different word types. So what's a word type? A word type represents essentially just like each of these things is a word type. Okay, so let's define a word type class now, and let's look at how it's. Word type is essentially very simple. It has a phonemes and it has a weight. Data class word type, phonemes is a string, yeah, and weight is a phonemes is a string. And weight is integer. That's it. Now, what do we have here? We essentially have, so essentially, and it can be read from JSON. So it does have a companion object, and it has this read from JSON stuff. So by the way, you can see how the IntelliJ IDEA code completion suggests the names of the function parameters. So it sees that there are other functions which have the JSON node parameter with the type of JSON node, and it offers this here as well. So like this idea that having types before, so there's this idea that having types before names, like in Java, it helps implement code completion, because first you enter a type, and then you can choose the name of the variable based on the type, and the completion can generate the name from the type and offer it automatically. And as you can see, this is not necessarily the case. So in many cases, we can still offer completion, even though we have types on the right in Kotlin. And it's very simple. So it has phonemes and weight. String, this text, and weight as int. Yep, that's it. So now, what's a phonotactics? Phonotactics is essentially a map of those. So in the C++ implementation, phonotactics references a phoneme table, so we are actually probably going to pass in this reference. And so I'm going to use introduce variable refactoring here to, here you see that we are actually creating the phonotactics object in the current code before we create a phoneme table. And now I'm going to have to do this before we create a phonotactics. And so I'm introducing this variable, and I'm using the move statement up action to move this a few lines up. And now we can actually pass in this parameter here. JSON, and I made a mistake here. Yeah. And we still need a phonetics for the language constructor. So yes, and here it's going to be a map. Yep. Okay, so what do we have next? The next we have, so I actually kept writing this code and I forgot where I stopped. So essentially the phonetics is essentially just a list of word types. And the phoneme table. So we just returning a new phonetics of a phoneme table. Phoneme table and value map type read from JSON with okay, wonderful. So now we actually have the ability to generate a word. So we now have enough data in our model to generate a word. So I'm going to actually generate the very simple word that we have here, just show how it works, and probably at that point I'm going to end the today's stream and I'm going to continue this story in the next video. So let's do this. So in this phoneme table we have this generate method, which receives an ID of a phoneme and returns the actual corresponding text. So the implementation, I believe, is very trivial. We're just choosing the yep. We're just choosing the random element. So let's add this method to the generate class, to the phoneme set class. So we have this read string, and it returns going to make this a function. Random element. So I'm going to pull this up on the top level. And I'm going to make this, first of all, it's a generic function. So it works on any list. And I'm also going to make it an extension function on the list. So I'm going to use this very easily. I'm going to use the intention action convert parameter to receiver. And now, now on every list, I just have this random element function. Now let me check if I actually implemented this correctly. So this returns, yes, so this returns double value from 0 to 1. And so I'm multiplying this by size, getting from 0 to element size to the number of elements. Yes, so 0 to the number of elements, then I'm dividing this, then I'm taking this, then I'm just truncating it to the integer, and so yeah, I'm going to get as many choices as, get as many possibilities as there are elements in the list. So now this becomes as easy as, yay, exception. Interesting. Report to JetBrains. Okay, so at this point I'm going to start writing tests finally. So I'm essentially going to reproduce the situation that I have here in tests. Yeah, so surprisingly enough, IntelliJ IDEA still uses JUnit 3 as the main test framework. So it does not use these add test annotations as a rule. So I'm not very fluent in the use of those, even as simple as they are. So I'm just more used to writing tests that do not use this annotation. So in the test, I'm going to create a very simple phoneme set of one phoneme set with one phoneme. The phoneme O. List of. And I'm going to insert true. So this is not a very interesting test, but still I'd like to have it. So this is actually a test for the phoneme set generate. Just to make sure that it all makes sense, I'm going to run it. It passes surprisingly enough, and now let's try a more interesting test. So I'm now going to programmatically create a phoneme table with, essentially I'm going to rebuild a very small part of this. Essentially I'm going to rebuild this rule in my unit test, and I'm going to try to generate the word and see what I get. So what do I do? First of all, I create a phoneme set. With a single phoneme once again to remove the randomness for our test, and I'm going to use the P letter this time. And I'm going to create a phoneme table which maps the P letter to this phoneme set. Okay. Now I'm going to do this. Now I'm actually going to create, now I'm going to look at the implementation of this underlying C code and follow it more closely. So what API do we have there? So we have the generate method. So we don't have a generate method we do have a generate method in the phoneme set class. And we do have a generate method with ID in the phoneme table class. And this method does what? This method does nothing very interesting, but I'm going to use this as well. So once again, this is going to be a test for and P rate P. So the parameter of this method is essentially the identifier of the group of phonemes. So for example, it can be either all vowels or all consonants or something like that. And the return is the sound that is actually going to be used in the word in our language. Create member function. Create equals generate. As simple as that. So of course, this is not a very good thing that I'm doing here with this double bang. Okay. Yes, so it actually has to be, it will be a string. So this is correct, the test fails correctly. So this is not a very good thing that I'm doing here, so I should instead be, so I should actually validate the data that it's all consistent, because right now if I don't enter some of the data in those strings in my JSON file correctly, then I will get an exception at runtime, and this is not very nice. But yeah, well, it's a game, and I'm still in control of all the data myself, so I can figure it out if something goes wrong. Okay, so the next thing is that we are actually going to have a generate method in the phonotactics class, which is more interesting finally. It's called generate word. Okay, so we haven't actually handled the weights of the word type. So the way it's handled here is very simple. So essentially, the weight of the word type determines how often it comes up in generation. So if the weight is like 6, so we will repeat this entry six times in the array. And then when we choose the random word type, then the higher the weight, the more likelihood that this particular word type will be chosen. But we will deal with this somewhat later. So I'm going to write the most basic test for now. So once again, now we're going to initialize the phonotactics. And the word is actually going to be pipe. And the generate word method does not exist, and I'm going to create it. It returns a string, and it returns an empty string for now. So now this starts resembling the traditional TDD loop more closely, so I'm usually not very pragmatic about following it. So I like test first development, especially when I fix bugs in Kotlin. It's always very nice to write a test before you write a bug, when you usually have some kind of repro steps that you can use, and you can turn this into a functional test and then run the test to make sure that, run the test and see that the bug see that the test correctly reproduces the bug. Then you fix the bug and run the test again to make sure that it's fixed. And this is a very nice flow. So what does the generate word method do? The generate word method gets a random word type. So I'm going to use, once again, so this is word types first. This is like the best way to choose a random element in the list, is to choose the first one. Okay, so I actually have a random element function, so I'm going to do that. Use that. And let's not return this. And then return So it's a string, so I cannot use it directly join to string on it, so I'm going to map this into a list of strings, and then join to string with a separator equals, with an empty separator equals empty string. Because by default the separator is something else. Yeah. So now the parameter of this lambda is a character, and if it's so I'm not going to extract this in a separate method. I'm just trying to use, I will just code this directly, and C is uppercase, then from table dot generate C else C. That's it. So I'm running the test again and it passes. So okay, I've been doing this for like close to 1.5 hours, so let me summarize what we have now. So we had this original C++ code, which consisted of a header file of 400 lines, and we had a CPP file of another 750 lines. So it's like over 1,000 lines. So of course there is a whole bunch of stuff that we did not re-implement yet. So there is like language model generation and like transformation process between different languages, but just in an hour and a little bit we have been able to write 140 lines of Kotlin code that re-implement, I think, half of the functionality that is in the C++ file. I think this is quite nice productivity and quite nice way to express the code, and you can see that there is very little redundancy in the code, so it's all maps very directly to what I want to say, and it's easy to write, and it's very, very nice to work with. So we have a successful test, and yeah, one last thing that I'm going to do now is I'm going to publish the code. So let me show you how we can do this. So I'm going to import into version control, share project on GitHub, and create API token. So I'm going to use my password authorization. So the original C++ code is not open source, it's in a private repo on Bitbucket, but for this one I'm going to make it public. Share. So now I have a whole bunch of stuff that should not be in the version control, like all the .idea directory with all the Gradle generated stuff. And yeah, this is the source files, initial commit. So now if you go to my GitHub, or if you just click on this link, so you see that this is the project that I just built. And here's the code. Okay, that's it for today. Thanks to everyone who listened to this, and thanks to everyone who will watch the recording, and signing out for now. Thank you, and happy Kotlin.